This conference will now be recorded.
Very good morning, students. So we were
This conference will now be recorded.
very good morning, students. We have been discussing ray optics, and today we are going to learn compound microscope. In the last class, we have already discussed about simple microscope, but when we learn compound microscope, we must be having some idea about the simple microscope as well. So for the sake of recapitulation, we'll discuss here once again the simple microscope part, and then it will be actually easier to discuss compound microscope once we discuss simple microscope. So today's class will be on both simple microscope and compound microscope. So let us start our discussions today. Before we start learning about simple microscope directly, let us learn few terms which we are going to use here. One is least distance of distinct vision. Okay, so this is related to human eye, and the other one is magnification of microscope. So these two terms will be using while discussing simple microscope as well as compound microscope, and even in case of telescope also will be using these terms. Okay, I hope you know the basic use of microscope and telescope, etc. So microscope generally we use to see a tiny things in a bigger font, right? That means small object can be seen through microscope as a bigger one, like this. Okay, so if I have written a like this, when you see through microscope it will be like this. Okay, in bigger font we will see. So a small object can be seen bigger through microscope, and that is actually magnification. Magnification means a small object can be seen in a larger size or bigger size. And how much larger? At least in compound microscope it will be some 1000 times greater, 10 to the power 3 times greater than the object size. Okay, 10 to the power 3 times greater. Okay, in compound microscope. In simple microscope, at least 10 times greater. In simple microscope, we can see an object 10 times greater than the object, and in case of compound microscope, it will be 10 times greater than, sorry, 1000 times greater than the object size. So let us see what is called least distance of distinct vision. So it is the minimum distance. Least distance of distinct vision means it is the minimum distance. Okay, let me write least distance It is the minimum distance from the eye at which the eye can see the object distinctly and without any strain. Any strain in the eye. In the eye. Okay, so least distance of distinct vision, or sometimes near point also it is said. It is said near point. Okay, so least distance or the smallest distance from the eye at which we can see an object distinctly without any strain to the eye. Okay, and for a normal eye, it is actually denoted by D. Near point is denoted by D, or least distance of distant vision is denoted by capital D. For normal eye, normal human eye, it is some 25 centimeter. Obviously, it can vary person to person, but in general, it is 25 centimeter. And when a person grows old, then this this becomes different actually. Okay, because the power of accommodation of the eye becomes lesser or decreases, and in that case, this distance may go 40 centimeter or something. Okay, all right, so this is actually least distance of distant vision. So when we say that and denote that by D, you should understand this is 25 centimeter for normal eye. Okay, all right, so I'll just erase this. I'll now define what is magnification. Magnification or magnifying power, it is called magnifying power. Okay, so magnifying power of microscope, magnifying power of a microscope. Actually, this definition will be common for both the compound and simple microscope. So that's why I'm just defining this in the beginning itself. And it is denoted by small m. It is denoted by small m, just like linear magnification in case of lens. Okay. So this magnifying power is the ratio. Okay, let me just first write this in terms of sentence. Magnifying power of a microscope is defined as the ratio of the angles subtended by the final image at the final image and the object at I. Okay, at I. And when, so actually there are two things here. When the object and images, okay, so at least up to here it is fine. Now there are two conditions of image formation in case of microscope. One case, first case is when the object and image both are at the least distance of distinct vision, and in second case when the image is formed at infinity. So these conditions will come along with this. Okay, at least see here up to here will it will be common for both or all the cases. So M is actually angle subtended by angle subtended by sorry angle subtended by the image or the final image. I can write final image at I, okay, divided by angle subtended by object at I. So both the cases it is the I. Okay, the angle subtended by the image at I and the angle subtended by the object at I. Okay, so this thing should be remembered. Okay, now we'll move on to the simple microscope. So what is a simple microscope? It is just a magnifying glass having short wavelength. Magnifying glass means convex lens. Okay, just a magnifying glass. Okay, convex glass, convex length, so it should say here, having short focal length. So let me first write what is simple microscope. A simple microscope is just a convex lens. Convex lens of short focal length. Held close to eye. So magnifying glass is always held, or simple microscope is always held very close to the eye. Very close to the eye. Okay. Now we'll see. We have to actually, in exam also, you have to find out the magnifying power of a simple microscope. So there are two conditions when the final image is formed at the least distance of distinct vision. So this image is actually simple microscope. A simple microscope set or is said to have the image at least distance of distant vision. Least distance of distant vision. Okay, so when a simple microscope is said to have the final image at least distance of distant vision, then how would be the ray diagram for that? This figure is actually that ray diagram for that. Okay, so what is being done here? Actually, we know for a convex lens, when you keep an object, see if this is the focal length and this is the optical center O, if you keep an object in between focal length or in between the focus and the optical center, then there will be an image. That image will be virtual, erect and magnified image. Okay, so I'll just clear this definition of a simple microscope. I hope you have noted it down. I'm going to do a little bit of calculations here, and that's why I'm just clearing this space. See, when an object is placed, see in this case, when the microscope is set for having final image at least distance of distant vision, then actually the object is placed in between the optical center and the focal length, and in that case the convex lens will produce a virtual image, and virtual image will be erected and magnified. Look this figure, A prime B prime, this is the image of this object AB. So AB is the object which is placed within the focal length of this lens, convex lens. Okay, and this A prime B prime is the virtual image found by this lens. So this is actually one of the action of the simple microscope. And look, this eye is actually very close to the lens. So anything we measure from this lens, optical center of the lens, is equivalent to the distances or the measurement done from the eye itself, because the eye will be placed to very, like eye will be placed very close to the lens. Okay, so as I said, the image is formed at least distance of distant vision. So this is actually V here, D, you can see that. And what is U? U here is this. Let us say this is X, and both are minus actually, because we are going against the direction of incident ray. So both these distances will be negative. U is minus X, okay, and V is minus D. All right. Now if we define magnifying power at this case, so magnifying power, I hope you remember. I can show you the definition once again, because I have not erased that. See, it is the angle subtended by the final image at eye. Let me show you here. So the final image is this A prime B prime. It is subtending an angle at the eye, I means we can just take the optical center. So this angle is beta. You look here, this angle, this whole angle actually, this whole angle is beta. You can see that. Okay, so this angle is beta. So this beta angle is the angle. So I can write it here. This is beta by what? Beta by the angle. So this is the angle like angle that is subtended by the image at the eye. Now in the denominator should be the angle subtended by the object at the eye, right? So see, the object is so adjusted that, or we have to take the distance of the object, sorry, angle of the object when, like magnifying power, in this case we are defining when both the object and image is at the least distance of distant vision. So if you see this image, if you see this, sorry, object A, B, this A, B, just go here with this. See this A double prime B prime. So this is same as this like lengthwise, vertical lengthwise AB and A double prime B are same. Okay. So now I can just take the angle. So the angle this length make at the distance of least distance of distant vision. This is the angle alpha here. So this is not alpha. Look here. See, look here. This is actually, this is beta, the angle I'm showing here. But if I take this, AB at this place itself, then it will be wrong. This will be again beta is equal to alpha, right here. But we have to take this alpha angle, the angle subtended by the image when the image is at the least distance of distant vision. That's why we have to take this. So this angle, look, with the optical center, this makes an angle, this A double prime B prime, this is alpha. So I can write alpha here. I hope you are understanding. And since this alpha and beta are very small angle, okay, alpha beta, these are very small angle, so I can write, see, this alpha and beta are very small, very small. So can we write simply alpha and beta is equal to tan alpha by tan beta by tan alpha, because tan beta for a small angle will be beta, tan alpha for a small angle will be alpha as well. Now we'll see what is tan beta. Tan beta, see, tan beta is nothing but, see, this one, this angle is beta, right? So this is actually perpendicular by base, right? So A prime B prime by B prime O, okay, and tan alpha will be this one, A double prime B prime divided by B prime O, right? Look, this B prime O will actually cancel each other, and here we will get A prime B prime divided by A double prime B prime, and see, A double prime and B prime, this is same height wise, so I can write A prime B prime divided by AB. So AB, see the image height, if I say this is H prime and this is H object height, so this is actually the magnification, right? Okay. Now I'm sorry, actually there is a small mistake, I think. Just a minute, I'll just clarify here. There is a small mistake here. Okay, so tan beta can be written AB by BO. This one, okay, AB by BO, and this was all right. A double prime B prime by B prime O. Okay, now look, you can get it corrected. See, this A prime B prime, as I said, this will be AB itself. See, AB by BO, and this will be B prime O by AB. Okay, this will cancel each other, and you get BO prime. Sorry, B prime O. B prime O itself is. So B prime O divided by BO. So what is BO? BO is X minus X. So B prime O is actually minus D, and BO is minus X. Okay, so these two will cancel each other. So finally what we are getting, M is equal to D by X. Now you might be thinking, what is this X? We don't know this X, right? So we have to bring this X in terms of the three parameters, whether it is U, V or F. These three parameters, in terms of these three parameters, we have to bring this, okay? This magnification we have to write in terms of any of these three parameters, okay? Let us go to that direction. So we know V is here minus D and U is minus X. So from length formula, what we can write? 1 by V minus 1 by U is equal to 1 by F. Okay, anyway, F will be positive here. So that we are not going to change. So 1 by V we have got minus D, right? Okay, and 1 by U I'll write with the positive sign itself, and 1 by F is this. See, I have to replace D by X. So I'll multiply D both sides. So here you will get 1 plus D by X plus D by F. Okay, so from here you can see D by X will be obtained as 1 plus D by F. Okay, 1 plus D by F. So look here, then magnification of a simple magnifying power of a simple microscope, when the image is formed at the final image is formed at the least distance of distant vision, what we are getting in that case, the magnification we are getting as 1 plus D by F. When the image is formed at least distance of distinct vision. Okay, so this is the magnifying power, okay, for the simple microscope. Now we'll go to the other situation when the final image is formed at infinity. Okay, at infinity. Here one thing I just wanted to say, see, in case of the previous one, so magnification was 1 plus D by F. You look here, for a simple microscope, when you want to see an object at the least distance of distant vision, when like what should be your focal length. Okay, if you increase the focal length, if you increase it, then you know M is going to decrease. Okay, if you make it shorter and shorter, if you make F shorter, then M will increase. That means for a simple microscope, the desired thing is that focal length should be short. Focal length for better magnifying power or magnification. Focal length must be shorter. Okay, must be shorter or short. You can write that. All right. Now, in this case, when the image is formed at infinity, see, I have shown you here the figure itself. See, when it is possible with a convex lens, only when you keep the object at the focal length, okay, or at the focus. If you keep it at the focus, then the image will be formed at infinity. Why you do this? Actually, sometimes eye gets straight when you see image at least distance of distant vision. When you see object at large distance, then our eyes are relaxed and it is easier to view the image. So for that case, we have to set our microscope in such a way that the image is formed at infinity. So in that case, look, if I write the magnification, you know the image is formed at infinity, so the angle subtended by the image is this. There is no doubt about it, beta. Okay, and the angle we have taken for the object is alpha. So this is, you can see this. Okay, so this is the angle. So I can write this as tan beta by tan alpha. Tan alpha. So tan beta, what we can write tan beta? Tan beta from here itself we can write h by f. And for see, we are taking the object. So when we take the angle alpha, we always take the object at least distance of distant vision. So that's why this figure I am showing you here. The alpha, tan alpha is actually given by h by d. So you get d by f. See, when the image is formed at least distance of distant vision, then it is 1 plus d by f. Now, when the image is formed at infinity, it is becoming d by f. So less than 1. So it is having, see, if I say this is at infinity I, and this is actually least distance of distant vision plus 1. I'm sorry, minus 1. Okay, so minus 1. Minus 1. Magnification or magnifying power when the microscope is set for least distance of distant vision, that is actually 1 plus d by f, right? ml 1 plus d by f. And when the microscope is set for having the image at infinity, then it is d by f. So these are two magnification or magnifying power you should remember. Okay, now what are the uses? You will see if you go to the watch shop, the watchmaker actually use this simple microscope, and he just put this simple microscope exactly like at the eye itself. I think it is interesting to see. Sometime you can go and see how watchmaker use the simple microscope exactly near the eye. And see, this is, as I said, this is magnifying, simple magnifying glass. Sometime we use this for seeing the texture of the fiber, thread of cloth, engraving, details of stamps, or in the science laboratories we use this simple microscope. Okay, all right, we will just go to the compound microscope now. See, what is compound microscope? Compound microscope actually has two lenses. Here, if you see the construction, so there are two lenses. Okay, one is called objective lens. Objective lens. This is actually the lens. This is the lens situated near the object, which has to be seen in the magnified image. Okay, so it is placed near the object. That's why this lens is called objective lens, and it has actually very short focal length, very short focal length, short focal length, and second point is it has very small aperture, very small aperture, very small aperture. I'll show you the figure and then I'll figure it out for you. Now, what is the eyepiece? So there is another lens or the second lens that is called eyepiece. So it is actually placed near the eye. Okay, it is placed near the eye. Okay, it has focal length larger than focal length. Suppose this is focal length for objective is f4 and focal length for the eyepiece is fe. If e is little greater than fo, and aperture is actually greater. Okay, aperture is greater than objective. Okay, greater than objective. Now I'll show you here. See this figure. So this is objective. So this has small aperture. You see this small aperture, and it has actually short focal length somewhere here. Okay, somewhere here, short focal length. Okay, very short focal length. Whereas this is the eyepiece, which has larger aperture. You can see this like this, and it has larger focal length somewhere here, little greater. Okay, somewhere here. So this is about construction. Now the distance between these two lens and like these two lenses is denoted by L. This is actually these two lenses are actually set at the two ends of a tube. Okay, they are actually held at the two ends of a tube, and this length can be actually altered by using this L can be changed by crack and pinion. Sorry, crack or rack and pinion. Sorry, rack and pinion. Rack and pinion and pinion arrangement. Rack and pinion arrangement. Okay, so what is this length? Length is length of the tube. It is called length of the microscope itself. I think it is called length of the tube length. It is called tube length, or distance between the objective and eyepiece. Okay, this is tube length L. So these are few things. Okay, here it is shown. See focal length up to here somewhere. Here focal length is here, this much. Okay, this is the U, the objective. Sorry, the object distance, okay, and this is V here. You look here for the first lens. So from this figure here, actually we are going to find out magnifying power when the image is formed at least distance to distant vision for compound microscope. See here, there will be two. There will be actually see how it works. First, this objective will see the object. Then an image will be formed by this objective. Somewhere here you can see this A prime B prime. So AB is the object which is seen by the lens, and image is formed. See, this is real and inverted image. Real and inverted image will be formed A prime B prime, and this image will be formed is in such a way that this image will act as object to the second lens, that is the eyepiece, and the position, object position, this one will be actually within the focal length. See the focal length FP here, see the focal length here, but this is the image is formed within the focal length for the eyepiece. Then what will happen, as you know, there will be a virtual image formed on the same side of this eyepiece, same side of the object, and it is erected. See, this is the object, so erect image will be this side only, okay. So this actually eyepiece is working as eyepiece is acting as a simple microscope here. Simple microscope, right? See, we have seen that here. See, when the object is placed within the focal length, okay, within the focal length of this microscope, simple microscope, it is actually forming a virtual, erect, and magnified image. So the eyepiece is actually doing the same job. Just before that, this arrangement is there because see, this will give some magnification, and this will magnify further. See here, this is the object size. So image size is at least 10 times greater. 10 times greater. Now this is object, it is actually 1000 times greater. 1000 times of A prime B prime, isn't it? So this is why there are two lenses, and since there are two lenses combined together, it is called compound microscope. Okay. So let us see how here we can calculate the magnifying power in this case. I have told you the working principle here. What is done? See, in the first case, for the object, objective lens, the object is placed just little beyond the focal length. Okay, it is actually outside the focal length. Okay, the focal length is somewhere here maybe. So this is A4 here. So it is just placed nearby that, but it is beyond the focal length. So that's why it will produce a real inverted but magnified image. Okay, and this image will be acting as an object to this eyepiece, and since this image is formed within the focal length of this eyepiece, this eyepiece will act as a simple microscope and produce a virtual. It will produce a virtual, erected, and very, very large image or magnified image. So here, magnifying power, as we have defined in the beginning itself, so it is the angle subtended by at the eyepiece, sorry, eye at the eye, because see that this is always actually you have to take the final image, not this image. So this image is, see, eyepiece and eye is kept like here. The eye is little bit away, but in general, practically the eye will be very, very near to the eyepiece. That's why this center of the eyepiece E, and this eye is taken as the identical point. So whatever angle or distance we measure from this E and I will be the same. So this is alpha. Okay, I hope we are actually going with the same definition and similar understanding. So this is the image. You look this image. So this is actually making angle beta. So tan beta, we can write this as tan beta by tan alpha. See, in this case, actually the image is formed. Both image and object are actually thought to be at the least distance of distant vision. Okay. All right. So since tan beta can be written as h prime tan beta can be written as h prime by a prime, sorry, h prime by this u. Okay, so ue, actually this distance I'm taking as ue and tan alpha can be written as h by d, as I was showing you all the way, because the object is actually taken that it is placed or so adjusted that the object is at the distance of distant vision. Okay, less distance of distant vision. So this is actually h prime by h into d by ue. Ue means this one, object distance for the eyepiece. And what is h? H is the object height, ab, and h prime is the image height. Image height, this one. Okay, this one. Along with that, see, this one is actually, this is the image, see, magnifying power for a simple lens. Okay, magnification by simple lens. This is actually by objective lens, and into this d by ue. Now we have to find out what is ue. Okay, or d by ue is what? For a simple, see, this is actually this is for a microscope at least distance of distant vision. What it would be? It will be 1 plus, we know for a simple microscope it will be 1 plus d by f. Okay, d by fe. So this is the magnification by the microscope, simple microscope. This is simply by objective. Okay, so I can write, see, this is mo into me. Me is the magnification produced by the eyepiece, and mo is the magnification produced by the objective lens. So what is mo? Mo is simply, we can write u objective by v objective. I'm sorry, this is v objective by u objective, or h prime by h, and me is simple microscope, right? For least distance of distant vision, we know this. And which one is acting as simple microscope? That is the eyepiece. So that's why we can write that. Okay, so m is equal to mo into me. Now we'll just go for the second part. Second part, you look here, when the final image is formed at infinity, and when it can happen? Only when this, see, this objective produces an image exactly at the focal length of this eyepiece. I'm sorry, this is actually, this is wrongly written here. Eyepiece is this one, and this is objective. Okay, so objective has to form an image of this AB. Okay, so for that case, magnifying power can be written directly here. You know this, what you have to write here, actually, this will be again MO into ME. So MO is again the same thing, H prime by H into this ME will be, see, for angular magnification due to eyepiece will be D by FE. D by FE, okay, D by FE. And see, magnification due to objective, see H prime and H, right? When the when the object AB is placed very close to the focal length of the, very close, even in case of this also itself, previous case itself, we can just say when the object is kept at very near to the focal length of the objective lens, then I can write UO as minus FO, and similarly the object will be the image will be formed by the objective exactly very close to the lens eyepiece here, very close to the eyepiece. So this distance, actually the VO will be L. Okay, so this MO can be written, in that case it will be written actually, see, it will be VO by UO, right? So if the object is placed very close to the simple microscope, objective, then the image will be formed very near to the eyepiece. So VO will be L and this will be minus FO, focal length of the objective. So you look here, what we can write, this can be written as minus L by FO whole into 1 plus D by FE. This is actually final magnification. And as you know, for a simple microscope, when the image is formed at infinity, then the image like magnifying power will be D by F. That is what we have already seen. So we can write it here. Say H prime by H, actually L by FO. This is not going to change, and this is D by FE. Okay. So this will be magnification when the image is formed at infinity. So for compound microscope, there are two settings. When, so I'll write M is MO into ME. This will be minus L by FO whole into 1 plus D by FE. This is when image formed at D. Okay, this is what it is. Now, second point, when image formed at infinity, this M will be, see, this will be for microscope at infinity. When image is formed at infinity, this will be simply D by FE, and this is not going to change, L by FO into d by ap. So these things you have to remember. So as I said, magnification of a compound microscope is actually some thousand times, okay, 1,000 times or 100 times greater than simple microscope, and 1,000 times of object the size of the object, size of object. Okay, so I think this is all of what we have discussed today. Okay, so we'll stop it here for today. Next day we'll learn about telescope. Okay, telescopes. And in the telescope there are two things. One is astronomical telescope, another one is astronomical. And another one is terrestrial. I think terrestrial is not there in our syllabus, both in NEET and JEE. So we'll just learn about this in detail. And there will be another point, that is reflecting telescope, that is there in our syllabus. We have to read a little bit about that. Reflecting telescope. So these three things we will try to cover in the next class. So thank you for your presence. Bye for today.